Hello guys, today we want to start our third lecture on transform calculus and partial differential equations. Still we are in chapter 4. So in this lecture I want to talk about linearity of Laplace transform, and then we want to talk about sufficient conditions for existence of Laplace transform. Okay, so Laplace transform is a linear transform. What does it mean? It means that if you have, for example, a Laplace transform of alpha, which is a constant, times ft, plus beta, which is another constant, times gt, so it's equal to alpha times Laplace transform of ft plus beta times Laplace transform of gt, or it's equal to alpha times f capital S plus beta times g capital S. So f capital S is Laplace transform of ft, and g capital S is Laplace transform of gt. So in this case, alpha and beta, so they are two constants, so are constants. So we can use linear property of Laplace transform to solve some examples. So in this case, we are not required to use a definition of Laplace transform, so we can easily use it based on the formula and linear property of Laplace transform. Let's solve one example. For example, we have to find Laplace transform of following function. The function is 3t plus 8 times e to the power of 2t minus 4 sine 4t plus 6. So if you want to find Laplace transform of this function based on definition, so it takes a lot of time. For example, if you want to find Laplace transform of ft based on the definition, so what you have to do, you have to say the integral from 0 to infinity e to the power of minus st times ft. So ft we have is 3t plus 8 times e to the power of 2t minus 4 sine 4t plus 6, so times dt. So you have to find this integral, so it's so long integral. As a result, we use linear property of Laplace transform, and we can use the Laplace transform. In the exam I'm gonna give you one table, and in this table you have Laplace transform of most of the functions, so you can use table to find Laplace transform of other function as well. For example, in this case, if you want to find Laplace transform of ft, it's equal to the formula sheet and all the formulas. So I posted on Moodle, so you can have access to the formula sheet to see how it works. So Laplace transform of ft is equal to Laplace transform of 3t plus 8 e to the power of 2t minus 4 sine 4t plus 6. Based on linearity of Laplace transform, so we can say that it's equal to 3 times Laplace transform of t plus 8 times Laplace transform of e to the power of 2t minus 4 times Laplace transform of sine 4t plus 6 Laplace transform of 1. So you already know that the Laplace transform of t, so it's equal to 1 over s squared. As a result, so 3 times Laplace transform of t is equal to 3 over s squared plus Laplace transform of e to the power of 2t, so we already had it, so it's equal to 1 over s minus 2, so we have 8 here, so it's 8 times 1 over s minus 2 minus 4 times, so Laplace transform of sine 4t, it's based on the formula that we found before, so it's equal to 4 divided by s squared plus 4 s squared, which is 16, plus Laplace transform of 1 is 1 over s, so we have 6, so we have 6 over s. So if you want to simplify here, so you have 4 times 4, so I can say it's equal to 16. So it's Laplace transform of this function, so we used linear property of Laplace transform to find this solution. So now we go through the next part. In this part, we want to talk about sufficient conditions for existence of Laplace transform. In order to know sufficient condition of Laplace transform, so we have to know two concepts. The first one is piecewise continuous function. So we have to know that what piecewise continuous function is. A function is called piecewise continuous on an interval if the interval can be broken into a finite number of subintervals on which the function is continuous on each open subinterval. The interval without its endpoints, and this function has a finite limit at the endpoints of each subinterval. For example, here you can see one function which is piecewise continuous. Based on this definition, so we should be able to just break function interval. What's the interval of this function? So it starts from here up to here. So the interval of function is from A to B. So it said we should be able to break this interval to subintervals, and on each subinterval the function should be continuous. If I break this interval to this subinterval and here, so in fact now we have 3 subintervals. It's the first one, the second one, and the third one. So now we have 3 subintervals, and on each subinterval function is continuous and has finite limit at the end point of each subinterval. So here we have one endpoint, so it has a finite value, and here we have another endpoint, so we have finite value. As a result, this function is continuous, piecewise continuous. So it's piecewise continuous. Oh, here I have forgot to have one U. Let me write correctly. So we have continuous. So it's piecewise continuous function. The first concept that we need for sufficient condition of sufficient conditions for existence of Laplace transform is piecewise continuous. So now we know how piecewise continuous function is. The second concept that we have to know is exponential order. Based on definition, a function is said of exponential order if there exist constants c, m capital greater than 0, and t greater than or equal to 0, such that absolute of ft is less than or equal m times e to the power of ct for all t greater than t capital. So if this condition is valid, so we can say the function is exponential order. Let's explain it with one example. Imagine we have a function like t to the power of 10. We want to see if t to the power of 10 is exponential order or not. If you just give me one set of c, m, and t capital such that ft, so here is t to the power of 10, is less than or equal m times e to the power of ct for t greater than t capital, then we can say 10 to the power of t to the power of 10 is exponential order. So here we have the plot. The blue plot is ft equal to t to the power of 10. So I assume I consider one set of constants, so I assume that c is equal to 1, m is equal to 1. As a result, m times e to the power of ct is equal to e to the power of t. The red plot here represents e to the power of t. So here you can see that between 0 to this point, so this point is almost, I think, 36, this point, 36. So from t between, if t is between 0 to 36, the blue plot is greater than the red one. So in fact, t to the power of 10 is greater than e to the power of t. But after 36, e to the power of t is greater than t to the power of 10. As a result, we can say that if c is equal to 1, m is equal to 1, and t capital is equal to 36, then t to the power of 10 is less than or equal to m is 1, c is 1, so e to the power of t for t greater than, so t capital is 36. So I could give you one set of c, m capital, and t capital. As a result, this function ft equal to t to the power of 10 is exponential order. You know, so maybe you can offer another set of c, m, and t. For example, in this plot, so the blue function again is t to the power of 10. Maybe you say I want to choose c equal to 2, m capital equal to 10. So in this case, you can see that when t is between 0 to this point is 11, I think, for example. So the blue plot, t to the power of 10, is greater than the red one. The red one is 10 to the power of 10 times e to the power of 2t. But after 11, so the red plot is greater than blue plot. So as a result, so I can assume that t is equal to 11. So for this range, you can say that t to the power of 10 is less than or equal, so m is 10, e to the power of ct, c is 2t, and is valid for t greater than t capital, which is 11. As a result, so you know you could give me another set of constants that this equation is valid. As a result, we can say that this function t to the power of 10 is exponential order. Now let's see another example. We want to see if we want to see if ft equal to e to the power of t squared is exponential order or not. So in this case, the blue one is e to the power of t squared. So you have to, based on the definition that we have, so you have to give me one set of C, M greater than 0 and T capital greater or equal to 0, such that the Ft, which is e to the power of t squared, less than or equal to m times e to the power of ct. So let's say, for example, one of you say that, okay, I assume m is equal to 10,000 and c is equal to, let's say, 2. As a result, m times e to the power of ct is equal to 10,000 e to the power of 2t. The red plot is 10,000. You know, 10,000 is just a random number, e to the power of 2t. So here you can see that if t is between, so let's say here is 4.1, this point. If t is between 0 to 4.1, then the red plot, 10,000 e to the power of 2t is greater than e to the power of t squared. But for t greater than 4.1, e to the power of t squared is greater than 10,000 e to the power of 2t. As a result, we couldn't satisfy this equation because, this equation should be valid for t greater than t capital. So we cannot find any t capital that this equation is valid. You can try different sets of c, m capital, and t capital, and for none of them, you can find e to the power of t squared is less than m times e to the power of ct for t greater than t. Maybe in a specific range, for example, here is 0 to 4.1, it's valid, this equation. But after that, it's not valid, but it should be valid for t greater than t capital until infinity. As a result, this function is not e to the power of t squared is not exponential order. If I want to tell you the rate of increment of function or growth rate of function, so the growth rate of function is like this. Growth rate. So at first it's constant function, then logarithmic function. After logarithmic function, so we have t to the power of n. So it's logarithmic function, so we have t to the power of n. After that we have e to the power of nt, and after that is e to the power of tn. As a result, if t approaches to infinity, for sure e to the power of t squared is greater than e to the power of nt. Doesn't matter what n is. Okay, so now we know the concept of piecewise continuous and we know concept of exponential order. So the sufficient conditions for existence of Laplace transform is the function should be piecewise continuous on the range of 0 to infinity. So here should not be closed, so it should be like this, 0 to infinity, and ft should be exponential order. But these two conditions are sufficient conditions. What does it mean? It means that if one function is piecewise continuous and exponential order, for sure we have Laplace transform. But maybe we can find a function which is not piecewise continuous or it's not exponential order, but still we have Laplace transform. So these two conditions are not necessary condition, they are sufficient condition. For example, for function, so let's say we have example, so we have ft equal to 1 over t squared, or t to the power of half. I can show it t to the power of minus half. So if I plot it, oh, such a ugly line. So if I plot it, so here we have t, here we have ft. The function is like this. When t approaches 0, it goes to infinity. When t approaches infinity, it goes to 0. So it's the plot. So this function t to the power of minus half is not continuous. So t to the power of minus half is not piecewise continuous. It's not piecewise continuous. Why? Because, you know, for definition of piecewise continuous, we said that the function at the end points, so one end point here is 0, should have finite limit. But here at t equal to 0, this function does not have finite limit. It approaches infinity. As a result, this function is not piecewise continuous, but this function has Laplace transform. So in next lecture, I'll let you know how we can find it. Laplace transform of t to the power of minus half is equal to root pi over s. So now we can see a function which is not piecewise continuous, but still we have Laplace transform. So it means that the conditions that we have, they were sufficient conditions, not necessary conditions.